Hi everyone, welcome back. And today, well, I can't tell you how excited I am because we're finally going into, quantum mechanics related content for nonlinear optics. Because you see, the name of this class is quantum electronics, and then it has already been more than 2 months, and then we haven't even touched quantum yet. So today, what we're going to do, okay, this is a individual. Well, this is a separate section that it's not related to anything we're going to talk in the next few months, in the next few weeks, but rather to explain, okay, what we have learned in the past 2 months. Okay, the idea, okay, the topic for today is how to get chi. Right. So from the nonlinear optics, well, we learned that the displacement field can be written as electrical field plus polarization. Okay, and then the polarization goes with, there's a linear one, and the definition of polarization here, P defined by N Q R. Okay, N is the number density of the charge. Q is the number of charge. Well, N is the number density of the charge. Q is the amount of the charge in your material, in your, for example, atoms or molecule. And R, okay, is the displacement of your electron or of your charge away from equilibrium place so that it generates a dipole. Okay, and this one we have talked about this at the very beginning of this class. And then also, but we never really truly use this equation because we know that the displacement, okay, of your electron is driven by the electrical field of the light. So in the past we have said that, okay, you can simply say that you can do a Taylor expansion of the polarization on the electrical field so that you get this. Okay, the first order is linear, second order is, and then you have third order, and you keep going. Okay, and then in the past we have kind of say that, okay, this expansion make a lot of sense, and then all these parameters you can measure them from experiment. But we never tell you, okay, how we can actually calculate these parameters, these coefficients. And here today, okay, we're going to introduce this idea of how to use perturbation theory in quantum mechanics, okay, and then to get chi2 and chi3. And what we're teaching here is only the method. Okay, we're not really going to calculate one material because the equation, once you look into it, the equation would be very, very long. The solution can be fill all of this whiteboard. Okay, so normally what will happen is you can use computer, okay, to write a code to actually calculate all these coefficients numerically. And perturbation, the perturbation method in quantum mechanics is kind of well developed. So I think you can even find package on Mathematica or on MATLAB. Now let's say a little bit of how we can calculate all this coefficient. What is the workflow here? Okay, so the key idea is to solve, well, number density and the amount of charge of the electron. These two are prefixed by your material. Okay, you really don't need to solve anything. The only important thing here is to solve the displacement in the presence of your electrical field. So the question here is that if you have an electrical field that can be written as this, okay, multiple frequency component. Later we'll show that this ikj term is not important in this calculation. Okay. Question is that if you have this field act on molecule or atom, what is the displacement generated by this field? And then to match the solution of here, right, to match the this Taylor expansion of your polarization here, so we must have the method we are going to use is perturbation theory in quantum mechanics. Okay, then what then will happen is that R will, through the calculation, will show us, okay, you have E, some coefficient, and then E squared, and then E to the third. And then after you're solving this, okay, you plug this back to here, okay, multiply NQ, and then divided by epsilon, then you get your coefficient of chi. Okay, so this is the entire workflow. The key, okay, is to get the displacement generated from the electrical field. Okay. Now the calculation of R, okay, the displacement field, the average displacement field, displacement of the electron is actually quite tricky in quantum mechanics. Okay, and because the limited amount of time we can spend on this class, I just can't reveal the entire quantum mechanics for you guys. So rather, I will give a very quick and very brief introduction of what quantum mechanics, what knowledge in quantum mechanics you guys need, okay, in this calculation. And then if you have never learned about quantum mechanics before, I recommend the MIT Quantum Mechanics online course. Okay, you can find it on YouTube, and just watch the first few classes, and then to build a concept of what quantum mechanics is. And if you have trouble understanding quantum mechanics, that is perfectly normal. Like I've never seen anyone that really can accept the concept of quantum mechanics in a few weeks, and we're only 1 week from the final exam. So okay, so what I'm saying is that adjust your expectation. Okay, don't expect too much when you start to learn quantum mechanics. So in quantum mechanics, the critical difference between quantum mechanics and classical physics, when you're calculating a variable, when you're calculating a variable or a physics attribute, is that in quantum mechanics, let's say in classical case, we describe electron as a particle, right? A particle has x and p. Particle has position and momentum. And then what you do is that you write down based on F equal ma. Okay, you write down your differential equations. You write down differential equations for position or for momentum, depending on which one you want. And then you get your solution, x equals to a function of t. Okay, and then you say, okay, I get the displacement of my electron. So this is how classical mechanics work. And unfortunately, in quantum mechanics, this simply doesn't work. Okay, and the reason is quite interesting, is that because when you're approaching certain regime, you no longer has a particle. The particle, the concept of the particle itself, to be honest, okay, the concept of the particle itself is actually questionable, because just imagine, we say electron is a particle in classical physics, but has anyone really seen a picture of electron as a particle? No, right? The idea that electron is a particle is just our projection of our current understanding of the world, and then we think, okay, everything is made of particle and then they can move, so electron must be a particle. But the fact is that electron doesn't obey all the laws for the particle. It actually obeys the law for the wave. Okay. So in quantum mechanics, what happened is that your electron is a wave, or let's say this: electron obeys the equation of motion for the electron obeys a wave equation. So you have a wave that is a function of x and t. Okay, just like your electrical field is a field, right? So here is a wave, but also in advanced quantum mechanics, you can treat this as a field, and then there's a second quantization, but we won't touch those. We won't touch those areas in this class. So it's a wave, and then and instead of F equal ma, you have Schrodinger equation. You have Schrodinger equation, governing the motion of this wave. Okay, and then the next, well, let's write that down. What the equation would look like. Later, I will explain why the equation look like this. And actually, in my undergrad class, we actually derived this equation. Well, it's not really a derivation, but it's a guess. Let's say 1D. Okay, one dimension you have sign here. Okay, Schrodinger equation. If you look at it, it's actually almost the same as our equations for the soliton, right? You have the first derivative of time, second derivative of space, and then you have a potential well here. And then, if you look at this, you think, okay, where the hell does this come from? It look absolutely absurd. Okay, later we'll justify this, and then you'll see this is very natural. Just very natural to write this down. And then in to be honest, in qualified exam, if the student is doing things with quantum mechanics in their research, usually at least we will ask, okay, can you write down a Schrodinger equation? If they say they forget, or if they say they can't, that usually means they don't truly understand what Schrodinger equation is. Okay, and then the problem, okay, if you look at here, an obvious question is, what exactly is a wave equation? And how can I calculate displacement using this wave equation? Okay, and this is actually the question asked in the very beginning when Schrodinger write down this equation. Schrodinger has trouble explaining this equation, and then later people find out, okay, this is more like a probability wave. So okay. The amplitude square of this represents the probability of finding electron at time t, right, at this time window, and then at this place, and at this position window, right? Find the electron at this time, okay, in between this time and between this space. And if you say, okay, now how does that help here? Okay, in quantum mechanics, people have proved that if you want to calculate the expected value of an operator or of an physics attribute, for example, in this case, is the R, right, a three-dimensional position. Then what you do is that you take your wave function, okay, its conjugate times this physics attribute, in this case, would be R. And you might wonder why this is an operator. Later we'll say this. Okay. And then multiply, not multiply, but act on the wave function itself, and then do integral from minus infinity to infinity. Okay, so it's like the way you can interpret this is that, okay, this times this is like a probability density. Okay, and then you multiply the value itself, which gives you the expected value. Okay, it's like the average, weighted average value. And of course, the interpretation like this is kind of classical. Okay, and it's not 100% accurate, because what will happen is this is an operator, and then this doesn't really mean a value here. Okay, but if you have trouble understanding this equation, you can just imagine, okay, probability density, this times this, probability, okay, probability density times your value give you the average. So the concept here would be very straightforward now, okay? The workflow will be very straightforward, okay? We use Schrodinger equation, we solve the wave function, and then we use this equation to calculate the expected value of R, okay? And then we'll plug this back in, and then we get all this coefficient. Okay, we expand. Of course, we need to expand R in terms of e squared, e to the third, and then you will get all this coefficient. Okay. Okay. Now next, let's justify, okay, this Schrodinger equation, and the way, okay, I try to do this is not to really prove it, okay, very strictly to you, but to show you that this really makes sense. Okay, so first you have to accept that electron is a wave. Okay, I know this is difficult, but what you can do is that you can Google electron interference or electron-Young's double slit experiment, and I think it's there's videos on YouTube that this is an experiment did by Hitachi company, the Japanese company, really showing you that, okay, if you send electron instead of photon to a Young double slit experiment, you will actually see interference pattern. So electron in that sense, it's really a wave. Okay, at least its motion is governed by the wave. So if there's a wave, then what's the simplest form of a wave? Right? We know that it's plane wave. Let's say this is the simplest wave. And notice here is because the wave function itself here, we call the quantum mechanics wave function here, it doesn't really represent a physical meaning. Okay, the physical meaning is when you do this conjugate square, it's do this amplitude square. So there's no reason to force your wave to be a real number. Okay, whether it's a real number or complex number, it will give you the same result as long as it's a solution to this Schrodinger equation. Okay, so the simplest form of a wave, a plane wave, actually tells us a lot of things. Okay, so first of all, we have said in many cases we say that the energy of a photon is h bar omega. Okay, and this is actually assumed by Albert Einstein in 1905 or 1906 to explain that why when photon hit a metal that you need certain frequency to have the photon knock out an electron to form a current. And so this is the idea. Okay, h bar omega is the energy of a photon. And then also from there we know that the momentum, okay, if you divide it by c, okay, the momentum of a photon will be h bar k. Okay, so this is energy, this is momentum. So now the idea is that if we assume, okay, because photon and electron are both waves in quantum mechanics. Okay, so if we assume that the form of its energy and momentum should be the same, right? If they all obey the same wave equation or all obey the Schrodinger equation, there's no reason that their very fundamental expression of energy or momentum should be different, right? So now, how do you get the energy from a wave? How do you get the energy from a wave? What you can see is that if you do partial t on a plane wave, okay, partial t on the plane wave, what you get is minus I omega coming out in the front, and then the plane wave itself, right? So then you get omega, right? You get omega. So what you can do is you can multiply h bar, okay? It gives you a h bar here, and multiply I times I here. Then this is minus 1, and minus 1 cancel with minus 1. Okay? So what this simple calculation tells us is that if you do a time derivative of a wave function for the plane wave, okay, this is only true for the plane wave, and then times IH bar, it will give you the energy of the plane wave, multiply your wave function itself. Okay? Multiply your wave function itself. So it seems that this operator here, right, because it's a differential, so it's actually an operator. This operator seems to give you the energy, okay, of your plane wave. And you can imagine, okay, because Fourier transform, all the wave can be expressed as a sum of many plane waves, then this must be true, okay, in some degree, this must be true for all the wave. So then what you can do is say, okay, this is energy. But we know that energy can be also written in a different form. That is, the momentum, this is a kinetic energy, plus the potential energy, right? This is also energy. This is energy. This is also energy. And this has wave function. And also I put a wave function here. And then this is something that Schrodinger did, is that he assumed this is true for all the wave. And so he removed the thing in the middle. Okay? He assumed that this gives you an energy times a wave function. This is, by definition, from classical mechanics, this is the energy, okay? Also times a wave function. Let's write it down here. So what Schrodinger equation is energy equals energy. Okay, energy equals energy. It's that simple. And this is the idea of how Schrodinger built this equation. You don't have to, well, if you don't understand this, when you look at this, you might think, okay, this is really, like how can someone figure out an equation like this? But this is actually quite simple. Now, the next question here is that the main trouble here, if you look at this equation, the main trouble here is that what is momentum, right? We never really identify momentum. Here we say that the wave function is a function of place and time, x and t. So it's relatively simple to write down the potential well, okay, as a function of x, because x is, used as a variable here. But there's nothing say about momentum, right? There's nothing say about momentum. You can't really, at this point, there's no way to get from this wave function to the momentum. So that's how this is going to get into the play, okay? So we know that momentum can also be written as h bar k for a wave. So how do you get h bar k for a wave, right? And again, we use the plane wave assumption. You can see that h bar k can come from you do a partial. Let's see, let's not use z, right? Because our wave is a function of x. Let's say x. Okay. want to get k out, so you can do partial x psi naught, right, on this plane wave. Then what you will get is you will get ik in the front. And then you will get multiply your wave itself, the plane wave itself. So to get h bar k, you multiply h bar on both sides, and then you divide it by I. Okay, you divide it by I. So this operator gives you h bar k, gives you the momentum. So that's why in quantum mechanics, okay, this is just an argument. That's why in quantum mechanics, your momentum is actually an operator, right? It's differential on position. Okay, momentum equals to h bar divided by I partial x. Okay, so that's why the Schrodinger equation eventually looks like this. What it is that you plug this back, h bar square, I have a square, so you have minus 2m partial square partial x plus vx, entire thing, act on psi. Okay, so first order differential on t equals second order differential on x plus your potential energy. Okay, and so this is how you get the Schrodinger equation, and then this is how you express the momentum, okay, in here. And the momentum in our case really doesn't matter because we calculate r, right? So what we really need is to use this equation, and then derive the wave function, and then do this integration, and then give you the expected value of r. Now we move the Schrodinger equation here, and then our target r, how to calculate r, we move it to here. And then so from this point now, okay, we're going to start to use perturbation theory a little bit. Okay, so first is that let's write down. Let's say there's an atom. Okay, there's an electron, right? There's atom, there's an electron. And this is simply, for example, hydrogen atom. And of course, you don't use hydrogen atom or hydrogen molecule for nonlinear experiment. So the actual atom is a molecule is much more complicated. So what we do is that, okay, for each molecule, for each material itself, it will have the electron, the outside electron, the active electron, would have an effective potential well, okay, from the core, okay, from the core, and also from other electrons. And what we do is that we assume that this one is H naught, Hamiltonian. H is Hamiltonian, which means the original momentum and potential well for the atom or molecule without applying this electrical field, right? Without applying this electrical field. And this is, really doable, right? This is really doable. For, you have a material, just write it down. Okay, this is really doable. And then what we do is that we consider the electrical field. Okay, the electrical field when you have light, right? There's the electrical field. Of course, it's oscillating. There's an electrical field acting on the electron. And when you have an electron in the electrical field, you have potential energy, right? You have potential energy. So that here you will have, because it's electron, so there's a minus sign here, E. And then your potential well is well, your potential energy is your position r times the electrical field itself. Okay, notice that the electrical field here is a function of time and position. And this is the potential energy of electron in electrical field. And what we can do is that we can treat this as, a perturbation signal. Here. We can say that this part is much, much smaller than whatever the energy, you impose on the electron from the external field is much, much smaller than the potential energy, the scale of the potential energy of the original atom or molecule. This actually makes a lot of sense, right? Because think about it: if this term is on the same magnitude as the original energy, then what it will really do is that it will pull the electron away from its original orbit and then become almost loose, and then you can get some free electron out. And this is possible, in some experiment, but in the experiment that we do in UVA and then also in most other labs, it almost never happened. Okay, so because we can say now this is, let's say this equal to, by definition, is H. Okay, and then so here to show that this is really a perturbation, what we do is that we define the H, these two in combine, equals to H naught, the original Hamiltonian, plus lambda times H prime, and then lambda much, much smaller than 1 in this definition. Okay, so that it kind of tells you that this is a perturbation. And also later, when we try to calculate the wave function epsilon, then what you can do is that you can have 1 lambda square and keep going. And this is now become a perturbation theory because lambda is much smaller than 1, lambda square is much smaller than lambda, and then you collect the same order on both sides of the equation, and then you kind of move from one complicated equation into a series of simplified equations, and then solve them order by order and give you this polarization. Okay. Now, to do that, the first step of perturbation theory is to solve the solution, assuming there's no perturbation, right? That's your starting point. Assume that the perturbation is really, really small. What would be the wave function look like? And this part is fairly straightforward. What we can do is that you can see the time derivative is on this side. On this side. So what we typically do is we solve for eigenstates or eigenfunctions, right? When you see a differential equation, then you can say that the eigenstates, because it looks like this, can be defined as a function of x, y, z. Let's say the nth eigenstate, because there could be many eigenstates, right? And then e to the minus I omega nt, right? When you do this, and then this will come out, and then on the left-hand side it will be h bar omega. And then you plug this back in to here, assuming lambda goes to 0, then you will have h bar omega n plus psi n x, y, z equals to h naught plus n x, y, z. So this has become an eigenvalue equation or eigenstate equation, right? Because an operator act on a wave function, give you a number times the wave function, right? So this is standard eigenvalue eigenstate equation. And then we can assume let's say we can assume that we know the solution. Assume solution is okay, u and x, y, z, t. Okay, we can assume that we know the solution. Or you can say x, y, z, okay, e to the minus I omega n t, right? Assume this is a solution and we know the solution. Okay, so this will be where we going to start, and then for any differential equation, right? This is a differential equation. We know that once you have the eigenstate that satisfy the boundary condition, that satisfy the differential equation, then any combination, or in quantum mechanics language, any linear superposition of the eigenstate is also a solution to this equation. Okay, then what you can do is that you can say, okay, in general, if in general there's okay, the solution would be a linear combination of okay, would be a linear combination of all the eigenstate functions. Okay, eigenstate function you get. And as a perturbation theory, okay, the idea would be, okay, we assume that none of these eigenstate functions are changed by our perturbation. None of them are changed, so they remain the same. What the perturbation do is that they change this superposition coefficient A, right? So instead of, for example, okay, this is quite easy to understand. Okay, suppose there are two energy level, 1 and 2. Okay, this is energy, ground state, upper state. So suppose there's no perturbation, then what the electron should do in the atom is that it should stay in the ground state, right? Because whatever in the upper state will dissipate and eventually come to the ground state. Then so in this case, okay, you have A1 t equals 0 equal to 1, A2 t equals 0 equal to 0, right? So it's all ground state and no excited state. But now suppose you have a field coming in, a light coming in, and then your electron absorb it, okay, and come up to here, right? There's some slightly there are some probability of it going from ground state to excited state. Then what will happen is that this now A is no longer 1, okay, it's A 1 minus something, let's say beta, and then this is no longer 0, this is okay, 0 plus gamma, right? So this is what really the physics picture of what we are doing here. Okay, the eigenstate is unchanged. The energy level of the atom is not changed by our electrical field, by our light, but rather, okay, when you have the light, what you do is that you change the electron where it stays in these states, right? Before you have a photon, well, it's on ground state. After you send in the photon, it's in a mixture of ground state and excited state. And if your photon is really strong, well, if you have many photons, if the light is really strong, then this can go completely into upper state, which is an absorption. Okay, so the concept here would be we need to calculate. Okay, calculate ALT. Okay. We need to calculate ALT, and then we also want to use perturbation theory, so we can say ALT, okay, perturbation theory has AL knob T, 0 order, lambda AL 1T, first order, third order, second order, and then keep going. Right, so what you do is that you're thinking, okay, the perturbation comes from this term. this term, right? And then lambda, okay, it determines the strength of the perturbation. So what you can do is that you do a Taylor expansion of all the, for each individual A. Okay, you can imagine now with the perturbation, that A must change from its original value. Okay, and how does it change? It changes by the Taylor expansion of lambda. And then when you do Taylor expansion, then you always have a coefficient, associated with the Taylor expansion, right? So this is how we express A. Okay, so the job here, okay, what we need to do is to calculate A, first order, second order, third order, and after we get all these values, then after we get all this, then equivalently we get the psi, and then we have the wave function, and then we can plug it in and then calculate the expected value of R. So this is the workflow. Okay, this is the workflow. Well, I don't know what's wrong with me, but I forgot to turn on the light when recording the video. So anyway, well, there's enough sunlight, this afternoon. So anyway, okay. So I wrote down all the equation we need on here, and then our task is to solve AL, okay, for all this L, the zero order, first order, second order, and go on, okay. And with this, then we can calculate the expected value of R. Now, what we can do is that we just simply plug in this, okay, plug in this into here, plug in this into here, and then on the left hand side, okay, on the left hand side, this equation into here. You see that there are, well, this is a time derivative, so you have a derivative of this and derivative of that, right? And that one gives you h bar L. So h bar omega L, this term, and there's a sum here, right? Sum L, ALT, UL, X, Y, Z, T, E minus I omega LT. Okay, so this is the first term and the second term is going on here, right? Okay, so this is the left-hand side, fairly straightforward. And let's look at the right-hand side. Okay, right-hand side. Right-hand side would be, let's see, plug this back in here, and then you will have the first term. Okay, and then the second term is the perturbation term. Okay, so here, okay, one thing that we notice is that H knob act on this is simply this times this, right? Because what is mu L? Mu L, we say, is the eigenstate of H knob, right? We say that because H knob UL XYZ equals to H bar omega L UL x, y, z, right? So these two terms really equals to each other. You see, and you can look at other coefficient here, al, e, and e. So these two terms, they can equal to each other. And then you can cancel it from left-hand side and right-hand side, right? So now the equation actually simplified to something quite nice. Would be sum of L, AL partial T, UL, X, Y, Z equal to the right-hand side, this one. Okay, so here I want to emphasize one thing is that, okay, some of you might look at, okay, here's u, e, u exponential. Okay, can I say that for this equation to equal each other, then this coefficient in the front must equal to this? You cannot do that. Okay, you cannot do that because now h, the Hamiltonian, okay, is not a number, it's an operator. So what will happen is that when this operator acts on this function, it's no longer UL. Okay, it might be other things. It might not be UL, right? So this might change the number of L here, right? So what really is that you have to expand this too, and then collect all the same eigenstate, the coefficient in front of all the eigenstate. I will show that in a minute. Okay. Now, to simplify this equation, whenever you see sum of L and then the sum has eigenstate in it, then what you need to do is to use the orthonormal condition in eigenstates or in eigenfunction. This is true actually for for differential, just general differential equation, and especially true in quantum mechanics. So what we have is that if you normalize UL very well, okay, if you do here and then you can normalize UL very well, then what you can find is that this is called orthonormal condition, is that if you multiply UL, UN, if you multiply two eigenstate and then do the integration, then this will become a delta function Ln, which means it's 0 when L not equal to n, 1 when L equal to n. Okay, the idea is this. Okay, this is the intuitive idea is that when you solve the eigenstate function, what you're doing is that you're the eigen equation, the differential equation, actually set a space, mathematical space, and this eigenstate function are the axes or coordinate axis of this space. So you can think of U and N, well, UL and UN as like your x coordinate, your y coordinate, and they should be orthogonal to each other. And the way to represent orthogonal is this. And this one you can imagine as, really imagine as a dot product of x and y, okay, equal to 0, dot product. Okay. Now, if you use this, you can use this to simplify this equation because on the left-hand side you have UL, right? Then what you can do is that you apply UN and then do on both sides and then do this integration, okay? And here let's see how we write it down. Yes. So L, left-hand side. Okay, you have, I think I forgot IH. just here. There's IH. Okay, there's IH here. So you have IH. Okay, differential here, and then integration of U N U L dx dy dz. Okay, you apply. So what it is that you apply. Okay, and then there's the time coefficient here. Okay, you apply UN conjugate, and then you do integration. Okay, then we know that because only when n equals to L, you have a non-zero value. So this one equal to IH bar partial AN partial T. This one goes away, and then e to the minus I omega nt. Okay, this is your left-hand side. So this is a way that to get rid of the sum. And this is really a quite standard mathematical tricks in quantum mechanics. And then the right-hand side, what you will see is that the right-hand side you have, you do the same trick here, and then you have L and lambda ALT integration. Okay, the reason this goes out of the integration is because they're not a function of x, y, z. They're not a function of position. So in reality, you can put this out in the front as well. Okay, and then you have multiply UN on the left-hand side, and then in the middle is H, and then you have UL. Okay, dx dy dz e to the minus I omega lt. Okay, and what is this? Right, this is an operator act on a function of xyz times another function of xyz. Right, so this is in the middle. Okay, this one would be a function of xyz, and then you integrate through xyz. Right, so if it's a function of xyz and then you integrate of xyz from minus infinity to plus infinity, then the result is that this will become a number. Okay, this will become a number. So by definition, we define this as a number of H and L. Okay, a number. So hat have a little bit of hat. This small hat means operator. No hat means it's a number or a function. Okay, so this one, okay, you can simplify it to lambda sigma L ALT H N L prime e to the minus I omega LT. Okay, so so left-hand side and right-hand side. Okay, if you write this down together, then what you'll get is partial A n partial t equals to, move everything to the right, then lambda divided by AH bar, and then sigma L AL T H N L, a number, and this is e to the minus I omega L minus omega n t. Okay, and this equation makes a lot of sense. What it tells you is that, okay, the absolute frequency, the absolute energy of your eigenstate doesn't matter. What matters is the frequency difference of them. Okay, so this is exactly the the picture as let's say there's a ground state, there's an excited state, right? If you want to absorb light from ground state to excited state, it really doesn't matter. It really doesn't matter what is the absolute energy, right? The only thing matter is the omega E minus h bar omega g. Right? The only thing matters is your energy difference, okay, between these two. Right? So that's why here the eventually the exponential term is a frequency difference. And with this equation, then you can kind of imagine what we're going to do, right? Left hand side is A itself, right? A, okay? So whatever order is whatever order you have. And the right hand side you have A, but you have a lambda, right? So on the right hand side, you are one order smaller than the left hand side. One order smaller than the left hand side. So the A knob, AL0 with time lambda, okay, has to equal to AL1 on this side. Okay, we'll show that in a minute. Now let's get to the final step of solving this A. Okay, solving this AN here. Okay, and just like any perturbation theory, what you can do now is just to plug in from this A, okay, the expansion of this, plug into here, then what you will get is you will get partial t, right, and then AN of different order, right, AN knob t plus lambda AN1 t plus lambda square AN2 t, okay, keep going. And then equals to the right hand side, which is this. That is, we keep sigma L, and then we have, let's put IH in the beginning, IH here, sigma L, and then you plug in L, AL into here, so I have lambda we put the coefficient in the front. Okay, so H and L e to the minus I omega L minus omega N t. Okay, this is a coefficient. Then plug in the A here. So you have AL. Oh, there's a lambda here, right? There's a lambda. Lambda from there. So the coefficient is lambda AL knob. Okay, very interesting. You have a lambda times the zero order, but here, okay, you have lambda times first order, right? So this makes a lot of sense. So what it means is that now you plug in the solution for the zero order, then you can get the first order. Then you plug in the solution for the first order, then you get the second order. So it really works as a perturbation theory. Okay, and then okay, plus lambda square, okay, because it's lambda times lambda, AL1 plus lambda the third, AL2, and keep going. Okay, keep going. So now what you do is you pick, okay, you pick the terms with the same order, and then put them into equations. So first is lambda zero order, so it's order 1. Okay, then there's only one term, that is this, partial t, a, n, zero order t goes to 0. Okay, so zero order, nothing changed. That's kind of our assumption because we assume that it's, this is just a perturbed term, so that the zero order should not change. And then we know that we use, initial condition that, when there's no light coming in, right? Initial condition, when there's no light coming in at t0, you have all the electrons are in ground state, right? This is just a natural assumption. So A1 knob goes to 1 and a n not equal to 1 goes to 0, right? This is boundary. This is initial condition, and because it's true because the derivative of this goes to 0, so this holds for all the time, all the t. Okay, and then we can move on to the second order. Second order would be partial t. We already cancel the lambda on both sides. an1 t equals to, you pick up the term on this side, it should be here. So IH bar sigma L AL knob T H and L prime, a number, right? E to the minus I omega L minus omega n T. Okay, and here we can, typically what we do is that we wait to the end to solve this, but because the first order solution is very straightforward, right? Only one is non-zero, right? So this one can reduce to, plug in here, reduce to IH bar A1 T, A1 T is just 1, right? Let's see, A1T, it's just 1, and then H and L is a number, e to the minus I omega L minus omega n T. L is 1 now, right? So it's omega 1. Right, so also n is, L is 1, right? So n1. Right, so in this way you kind of have a very simple solution now. The differential of a number gives you exponential of something, a number. So let's see. So we can quickly solve this. Let me double check. Okay, yes. So let's quickly solve this, and then you can collect all the term for lambda 2. And the idea is the same. We're not going to waste our time just on this mathematical details. Now here it's very, it's very tempting to just to say that it's actually very tempting to treat this as just a number and then do this integration on this t here. But the fact is you cannot do that. Let's see what is Hn1. Hn1 by our definition is U n x y z h prime U 1 and what is H? H here we say it's E minus E R times E, and E is really, let's say if we consider, right, E is really sigma j Ej E minus I omega j t plus ikz plus complex conjugate, right? So E turns out to be a function of time and also a function of position. So, but what we can do is that, now imagine this, the ikz, it change, the rate of the change is over one optical wavelength, right? Over one optical wavelength, you change from 0 to minimum to maximum and back to minimum. But when we do this integral, this is on the atom or molecules, right? And atom and molecules are much, much smaller than one wavelength. So in this integral, what we would do is that we assume that the z, okay, because the z in the integration, okay, the z for h prime, well, for this term to be non-zero, sorry, for these two terms to be non-zero, then the z is actually very close to 0 compared with the ikz, right? So you can say that the ikz simply doesn't change in this integration, right? So you can get rid of this. Okay, you can say, okay, we're at position 0, and because the atoms are very small compared to the wavelength, so this term doesn't contribute to anything. So if we do that, then what you will see is that, okay, there's still a time term, right? Time term. So this time term, although it doesn't get into this integration, but what it would do is that it would change your exponential term here, and then when you do the solving this differential equation, it will also change here, right? So here, what we can do is that we can, let's say, we can assume okay, we can assume R here. And then this E, let's say there's only one frequency component. Omega naught, let's say omega naught. Plus CC is just I omega naught T. Okay, so this is what you can write down with the approximation, get rid of the Z term, then this is, for single frequency, this is H prime. And you plug in to calculate this, and because E is just a number, or it's just a vector, okay, so you can get E prime out, E to the minus I omega T, plus E to the I omega naught T. Okay, and then in the integration, right, because this is a function of position, so this is also a function of position, then you get UN prime R U1 XYZ dx dy dz. Okay, so and we say this is a number, right? We say by definition, we can define, okay, this part is now really a number now. So E and then we'll give you an indices R1, N1, okay, N1. N1 means R doing this integration with UN and U1. And notice here, notice this one, okay? This term here, it has nothing to do with, it really has nothing to do with perturbation, right? Because you're taking the original wave function here, and then you're multiplying the R here, right? You're simply calculating the weight, you can say this is the matrix value of R, okay? So, so this is, determined by your atom or by your molecule, completely by your atom and molecule. It doesn't depend on your perturbation. So for this one, actually, you can look online. Okay, there's for some materials, it actually has a table, right, to get this number, to get this R number for you. Okay, and if you have this now, then just one thing is that if you want to include multiple frequency components, then you can say T, right, a function of T. It's the same. Okay, then you can plug this in. Okay, and then when you do integration, then the concept is very similar. You do the integral from 0 to t, and dt right. Do this right? And then on the left-hand side, you will get an 1 t minus an 1 0. Right, at time 0, we know that the initial condition is that the state is at 0. Right, so what you will get is you can eliminate this. Okay, except for n equal 1. Okay, you can eliminate this, and then it will equal to let's see, there's the IH bar here, a minus sign, so you can put I here, E, let's say put the position. No. R and 1, H bar, okay? And then this frequency times with this frequency also times with this, and we define, okay, let's see, we define omega n minus omega 1 equals omega n1. Okay, this is our definition, omega n1. So with this, then you do this integration and plug in the initial condition, and here we get e to the I omega n1 minus omega naught t minus 1 and then omega n1 minus omega naught plus e to the I omega n1 plus omega naught t minus 1 I n1 plus omega naught. I feel like this video has already been more than 1 hour long because I'm really exhausted. So you can cancel out the I here, okay? And cancel out the 1 here comes from the initial condition. 1 here, yes, comes from the integration from 0 to t. When it's 0, then its exponential term is 1. So this is where the 1 comes from. Okay. Okay, finally. Okay. And then here you see that the first order gives you E, right? The first order is proportional to E, the electrical field, which is great because, you know, in Taylor expansion, the first order is supposed to be proportional to E. And now let's think about the second order. Okay, second order. Second order, if you pick all the term here, then we're not going to calculate second order, but I want to show you, okay, what the second order would look like. Okay, this is picking up from the left-hand side. Yes, second order. And then pick up from here, second order is this one, right? So you have IH What's the number now? Okay, so the important thing here, is to notice that AL1, okay, AL1, which is solved here, this one has E naught in it, right? This one has an electrical field in it. And this one, the H, a number H here, you see that H here, also has E naught in it. Right? So what will happen is that, okay, when you're solving the second order of A, naturally your second order would be proportional to E naught square. Okay, so that you get the second order, okay, the E naught square, which make a lot of sense now because this is really the perturbation theory now. well, Taylor expansion now, right? The first order solution proportional to E, second order coefficient proportional to E squared. And then if you keep going the third, you will get third order E. Okay? And then let's wrap it up really quickly. Okay, then what you can do is that you can, now you have a solution for this one, and then you get R equal to psi R psi dr. Right, so you do this integration again, okay, using all this coefficient, and then eventually you will get a solution. Okay, and we're not going to calculate it here. It's really a little bit complicated. Okay, now let's talk about one thing. Okay, that this coefficient, right? So you can imagine, okay, if this coefficient become larger, then the term associated with E, okay, or E squared will become larger. Okay, and so now by looking at this, okay, one of course is depending on the material itself, right? Depending on the material, that you can't really change that much. You simply can look for different materials, and the E and H bar is the same. Then if for a given material, then the thing that really can help you, really explode your nonlinear coefficient is this term, right? It's this term. If omega naught equal to omega n1, then this term blow up to infinity. Okay, and blow up to infinity, and this means what it really means is that your, okay, let's say this is energy omega 1 h bar omega n. All right, so what it really means is that the input photon frequency is on resonance with one of your transition frequency in the atom. Then what will happen is that, okay, the atom will try to absorb this photon, and this interaction become very, very strong. Okay, very strong. And you might think, okay, now there's one obvious problem is that, okay, if it's really on resonance, then this whole equation become nonsense, right? Because AN would become infinite, and you can't really say this is a perturbation theory anymore. And also, it doesn't really satisfy the normalization condition for A. So this calculation, something is missing here. Is that if you think about here, what's missing in this calculation is a spontaneous emission, right? A spontaneous emission, right? In our calculation, there's no well, it doesn't include any term telling you that if you put electron at the upper level, it will spontaneously emit back to the lower level. Okay, and this is a balancing force for the absorption. Otherwise, every photon coming in will be absorbed, every photon coming in will be absorbed. So to do that, okay, if it's a spontaneous emission, then what should really happen here? There's a sign problem here. I kind of forget which one it is. I gamma and 1, right? So for this energy transition, okay, there's a spontaneous emission rate that hold this term not to explode to infinity. And to calculate that, you really have to use density matrix, which is probably too much for this class. Okay, and this is one thing to look after. Okay, and the other thing is that when you do all this calculation, eventually you will see, these frequency terms, they multiply together in here. Okay, all this A and A, and then you can see that when your frequency you can generate. And one thing you might realize is that for different frequency, well, although we usually write down as chi 2, chi 3. It seems that we are inferring that the chi is identical for all different frequency process, like some frequency, doubling frequency. But when you do this calculation, they have, there's a slightly difference in them. And so all of those can be determined in experiment. And then, so in most experiment, I'll be honest, in most experiments, you try to stay away from resonance condition, because if you're near the resonance, then there will be severe absorption, and if you don't have light, if all of the light is absorbed, then really the experiment doesn't have much sense, right? So when you stay away from it, then you can approximately say that the chi is the same for different frequency process, different nonlinear process. Okay, and so this is all for today. It's a lot of content, but I think it's kind of necessary for all of us who have learned nonlinear optics to know where the chi come from. Okay, where the chi come from. Use quantum mechanics, calculate R, and then use this equation to get back from R to polarization, and match all the order, and then you can get the chi. Okay, thank you.